Hi there, my name is Denny Lee. I'm a developer advocate at Databricks, and for this session, we're going to discuss how Apache Spark 3.0 and Delta Lake together enhance the reliability of data lakes. For this session, you will recognize the focus on SQL to addressing data warehousing like queries, as well as catalogs and metastores. Together with Delta Lake to provide ACID transactions for data reliability on cloud data stores, you can easily build your data lakehouses. So a little bit about myself. I'm an experienced distributed systems and data sciences engineer, helping to build the data platforms at Microsoft, including those at Bing, SQL Server, Project Isotope, the incubation team for what is now known as HD Insight, and Azure Cosmos DB. I was also the Senior Director of Data Sciences Engineering at SAP Concur. I'm happy to say, now I'm a developer advocate at Databricks. I also have been working with Spark since 0.7 and proud to be one of the co-authors of the O'Reilly book Learning Spark 2nd edition. You can download the ebook for free by going to the URL dbricks.co/getebook, don't forget the dash, so you can read and learn about Apache Spark, Delta Lake, MLflow, and Coalescing. I'll leave this link up here for a few more seconds so you can write it down and download the ebook now. So, as well, we recently published the VLDB paper on Delta Lake, high performance ACID table storage over cloud object stores. The paper dives into technical details behind how ACID transactions over cloud object stores, where we commonly build our data lakes, enables the data lakehouse paradigm. Data warehouse-like capabilities on low-cost, high-availability cloud storage. And please take a look at the paper because we dive into a lot of these technical details about the simplification of your data pipelines to things like time travel, schema evolution, schema enforcement, audit log transactions, things of that nature. So it's a great read and it just recently got published. So go to delta.io to download the paper today. So a little bit about the company that I'm part of, the awesome company that I'm part of. Databricks provides a unified data analytics platform to accelerate your data-driven innovation. We are a global company with more than 5,000 customers across various industries, and we have more than 450 partners worldwide. We're also the original creator of Apache Spark, Delta Lake, MLflow, and Coalescing. These open source projects that are leading the innovation in the field of data and machine learning, where we continue to contribute and nurture these open source communities. So come join us. And as we're talking about Apache Spark 3.0 and Delta Lake, a great resource is Xiao and Wenchan's Spark and AI Summit 2020 presentation, Deep Dive into the new features of Apache Spark 3.0. Both are Spark committers and PMC members, so you'll be hearing it from the source. But for this session, we're just going to focus on the performance and integration with storage system aspects. So if you want to dive deeper into all the other things that were included in Spark 3.0, after all, there were 3,400 PRs, definitely take your time to go ahead and take a look at their session. And recently, another great resource is actually the Delta Lake 0.7.0 and Spark 3.0 AMA with Barak, TD, and myself, where we answer the community's questions into the integration between Delta Lake and Apache Spark. For that matter, we're going to be discussing a little bit of those concepts in today's session, but just in case we didn't cover everything, go ahead and join us for the AMA. It's actually on the Databricks YouTube channel. If you just go there, it's on our Data and AI online playlist, where we, like I said, dive into Delta Lake 0.70 and Spark 3.0. So let's start with Apache Spark 3.0, where the whole community resolved more than 3,400 JIRAs. Okay, that's quite a few, right? Spark SQL and Core are the new core modules with all other components. They're pretty much built on top of these two. So, as I noted, in total, the pull requests for just those two things comprise more than 60% of what is basically Spark 3.0. So we're going to focus really on Spark SQL and Core. All right, that's really what we're going to do. So another way to look at this release is actually, I'll take that back. Wen-Chan and Xiao created this great slide that categorized all of the different capabilities, updates, and fixes as part of those 3,400 PRs. Okay, so there's a lot, to put it rather lightly. All right. For today's session, we're just going to focus on these two things. Okay, we're going to focus on performance. Okay. And we're going to focus on extensibility and the ecosystem, specifically data source v2 API and catalog support. Now, we're choosing these two things primarily, and there's a sprinkle of some of these other concepts, but we're choosing these two because we're talking about enhancing your reliable data lakes, or more specifically, the data lakehouse paradigm. And if you want to generally get to the theme behind everything, it really is about performance. So Spark 3.0 definitely does that. It's about ACID transactions, which is what Delta Lake provides. You put those two things together, and you also add in a data quality framework, which we'll briefly discuss, which is the Delta Lake medallion architecture. By putting these three concepts together, you're actually able to get that data warehousing-like capabilities for ease of RDMS management, yet you're running on top of low-cost, highly available cloud object stores. And so you get the best of both worlds between data warehousing and data lakes. And so that's why we're focusing really just on these two concepts today, okay? But please do note, there's a lot more to Spark 3.0, so I don't want to trivialize just those two things, okay? All right, so again, we're going to go focus on performance. And so the four major performance features that we're going to really dive into is about the including of a new framework for adaptive query execution and a new runtime filtering for dynamic partition pruning. And Spark 3.0 also greatly reduces the overhead of query compiler by more than half in support of a complete set of join hits. So we're actually going to focus primarily on AQE, dynamic partition pruning, and the join hits, because those are the key things. It's not to say query compilation speedup isn't interesting. It's just more a matter that it's relatively straightforward in comparison, okay? Because what we're going to do is we're going to dive into some of the details now, all right? So with adaptive query execution, this was actually available in previous releases, but it wasn't fully baked, right? We learned a lot from all the issues that were discovered as we placed AQE into production during Spark 2.x. So for this release, there's a lot of work that Databricks, Intel, and many other members of the Apache Spark open source community worked together to basically redesign the framework and resolve the issues that they had discovered. If I was sort of to go ahead and look at what was the Spark Catalyst Optimizer, well, in relation to the major versions of Spark, that is, okay, well, 1.0 sort of introduced the concept of rule-based optimization, as in we created a set of rules that would optimize how the Spark SQL engine would work. Okay, and that's also known as the Catalyst Optimizer. And by the way, if you're wondering who the picture is, the picture is Michael Armbrust here. He is the lead engineer at Databricks who led the development of what is now known as the Spark SQL engine. Okay, so if 1.0 was about rule-based optimization, Spark 2.0 or 2x, the 2x line, excuse me, really, this is where we introduce cost-based optimizations. And this is the idea of saying, okay, we're going to go ahead and calculate the cost from the logical plan into the physical plan, and then figure out if we can, based on that cost, choose the correct logical and physical plans and execute the query. Okay, so that's the concept of CBO, or cost-based optimization. Well, 3.0 introduced this concept now of running it at the runtime, right? And so basically you've run your rules-based, you've run your cost-based, but now at the runtime, perhaps you can make changes to the engine. And so this is this concept of Adaptive Query Execution Framework, or AQE. All right, so let's discuss this a little bit. So before I actually talk about the adaptive planning, let's just take a look at what the Spark SQL, or the Catalyst Optimizer, is. As you notice here on the left side, whether you're running Spark SQL queries or using the Dataset API or the Data Frame API, note that the Data Frame API is really just an alias to the datasets with a row, okay? What ends up happening as part of the Spark 2, what was really happened with Spark 2.x line was that we took the unresolved logical plan, we took into account of information from the metadata catalog, so in other words, like the tables that you have, built up a logical plan, and then optimized that logical plan. Once you've optimized that logic plan, we deliver multiple physical plans, and that's where the cost model kicked in, which is to say, hey, let's look at the physical plans and what's the cost for it. Depending on which one appears to be the most efficient, we'll select that physical plan, and then we're going to run the query execution. Underneath the covers, the query execution really is RDDs all over again with DAGs. Okay, and so that's the Catalyst Optimizer as a Spark 2.0 without the red lines. Okay, so now the red line that we're introducing as the 3x line is the basic idea of adaptive planning, is that we're going to re-optimize the execution plan using the existing rules of the optimizer and the planner after we collect more accurate statistics from the finished plan. Okay, so in other words, remember, when you build up a logical plan and attempt to optimize it, it's based on estimates of data sizes, the columns, how much memory it's going to use. And then it'll go ahead and execute these physical plans, right? Create multiple physical plans. And then again, the cost model will be really dependent on what those estimates are. And then it'll select that physical plan based on the on the cost model and try to execute. But when you do these executions, it isn't one step, right? There are usually multiple jobs, and even in those jobs, there are multiple stages in those jobs, right? So job stages, whatever the outcome of running the various tasks that are associated with it. The reason I bring this up is because, well, how about if you're running various tasks and you recognize the fact that maybe the table that you're looking at originally you thought was going to take 10 megabytes, now realistically only takes 5, right? Or maybe the other way around, you thought it was the original CBO thought it was taking 10 megabytes and now it's going to take 15 or 20 or more, right? These can have a potentially big impact on how efficient that plan will execute. So the purpose of the AQE is to say that, okay, we're going to look at whatever you're executing, we're now, because you've actually physically executed, you've actually run it, now you have more accurate statistics. Well, can we now use those statistics and adapt, alter, modify the plan right back up to the original logical plan and recognize the fact that maybe we can make things more efficient by taking account of some of the statistics that we sort of figured out, okay? So that's pretty much the context, all right? So let's dive into some of the AQE fundamentals themselves. Okay, so underneath the covers of AQA, there's really, right now at least, these primary optimizations as part of Spark 3.0. We're expecting more, by the way, okay? And there's this really, we're expecting more as time progresses, but right now this is out of the gate, the Spark 3.0, this is what we have, all right? And so a really, really good blog, by the way, is this one here, Adaptive Query Execution, Speeding Up Spark SQL at Runtime. So please do download, click on the link here to review the blog. And by the way, if you're wondering, yes, the slides that we have here are going to be available for you. So you're more than welcome to download them. We'll give them to you and you're good to go, basically, okay? So what are sort of the three main fundamentals? Well, it's about dynamically switching join strategies, about dynamically coalescing shuffle partitions, and dynamically optimizing skew joins. So you'll notice that we have a recurring theme of dynamics, right? In other words, we can change things on the fly, or hence the reason why we call the framework adaptive query execution, okay? Because we're adapting to new statistics, adapting to new data. So let's start with dynamically switching joins, okay? And with that, that's probably going to lead us to starting with broadcast hash joins. All right. So if you're not familiar with broadcast hash joins, one of the more common or most common performance tips to make your joins faster is actually to implement broadcast hash joins. Now, this graphic here that you're seeing here is not really realistic, but it sort of shows you more or less what the context is. So I want to be very clear, this is probably not the most accurate drawing of how a broadcast hash join works, or for that matter, joins and shuffling. But I hope you understand, we're doing this drawing to give you the context here, okay? So, for example, if you want to make your join faster, you're going to guide your optimizer to choose the broadcast hash join instead of the sort merge join. Okay, and to do this, you're going to specify spark.sql.auto broadcast join threshold. You're going to increase it or use the broadcast join hint in order for you to immediately make use of it. Okay, so what happens here is that if you think about it from like a data warehousing perspective, your fact tables, the grayish color on 4 different nodes. If you were to do a sort merge join, in essence, what's happening is that the dimension table is on one of the workers of the 4 workers you have, and you're going to have to shuffle the data back and forth between what's on the in the dimension table in green, and you have to shuffle to the 4 workers in this example in order to get the data there, okay? And then that's why a sort and a merge needs to happen in order for that join to kick in. What happens with the broadcast hash joins is that the dimension data basically is now floating in memory, and the reason you're setting or increasing the spark.sql auto broadcast join threshold is because if, for sake of argument, your dimension table takes up, let's just say, 8 megabytes of memory, well, if by default to 4 megabytes, by knocking it up to 8 or 10, then boom, automatically, if Spark is seeing that the SQL, the right-hand join of your table versus the fact table, in other words, your dimension table, if it's smaller than the broadcast join threshold, it'll automatically put all the dimension data in memory across all the workers. So now that's why you see on the right-hand side, the green dimension tables are floating all in memory. And so that way there's no shuffling between worker nodes, between the fact table data, which is partitioned across 4 different nodes, versus the dimension data, which is replicated across the 4 nodes. So this way the shuffling that's happening in the joins between the dimension table in green and the partition fact table that's in gray, it's only local, it's a local shuffle, i.e. local to that specific node. So that's great, right? I mean, why not just go ahead and use broadcast hash joins all the time? Well, as I just noted, like there's an auto broadcast join threshold. In other words, there's a limit on how much you can do it. So in other words, it's really, really hard to tune at times. You might even hit out of memory errors, right? And then if you do, then you get even worse performance because what ends up happening is the data ends up spilling to disk and you're going to get disk I/O all the time, all right? And even if it works now, it's really hard to maintain over time because it's sensitive to your data workload. So unless you've got a workload that doesn't change that much, which probably isn't a good thing, by the way, then it's going to be hard to tune. All right. So why can't you not always use them, right? Or why can't Spark just figure this out automatically? Well, there's actually a wide range of issues that impact Spark's ability to determine when to use a broadcast join, including things like missing or incomplete statistics, or if the file size does not match the actual data volume, such as when you're working with compressed files, or if the file format is column-based. Other reasons include if you have complex queries that contain black box UDFs, resulting in complex query fragments. Basically, these are examples that make it really hard to estimate the actual data volume. All right, so because it's hard for us to calculate the actual data volume, well then we're sometimes going to get it wrong. For example, if you've got a compressed file and you think based on the original estimate statistics that it's only going to take up 8 megabytes, but then it's a compressed file, so you find out in fact it has a 10x compression, so in fact it's going to take up 80 megabytes. What happens is that the broadcast hash join is trying to shove everything to memory, but because it can't, it'll actually leave everything on disk. So now it's splitting the disk, and it's going to go. There's going to be a lot of disk I/O. All right, so how does this work? Well, broadcast hash joins are often the most performed because one side of the join can fit into memory, just as I've been talking about. So Spark automatically utilizes the broadcast hash join based on the estimated size, right? That's what I was referring to in relation to that broadcast threshold. So the example on the left is the table on the right-hand side is estimated initially to be 30 megabytes, okay? Which is larger than what is available on the worker nodes, your broadcast threshold of, let's just say, 10 megabytes, all right? But how about if in reality, it's actually only 8 megabytes, which is, under our broadcast threshold. In the past, the original sort merge join strategy would still be implemented because it did not take into account of the new statistics. So because it already assumed based on the estimates that it was 30, so it's just going to do a sort merge join. But with Apache Spark 3.0, what you have here is AQE replans the join strategy at runtime based on the updated statistics. More specifically, Spark first executes the leaf stages in a query and collects the stats from the shuffle operators, which materialize the query fragments. So you can see the actual size of stage 2 is actually much smaller than the original estimate. That's the 30 to 8. And because the right-hand side is much smaller than the broadcast threshold, we can then re-optimize the remaining plan and change the join algorithm now from sort merge join to broadcast hash join. So pretty cool. So now that we're able to deal with dynamically changing join strategy at runtime, the next big issue is dealing with a large number of partitions, right? It's great that I can join, but how about if I've got way too many partitions? Don't forget, the default for a join in Spark results in 200 partitions. And, while that may be appropriate for very large data sizes, for smaller or even intermediate tables, that number may be way too large. So instead of taking on the overhead of too many partitions, because that will result in small network fetches, a lot of them, resulting in saturating network I/O, and to avoid you needing to manually modify the number of partitions for each and every join, perhaps maybe AQE can dynamically coalesce those smaller partitions into a few larger ones, right? After all, I'm pretty sure none of you enjoy constantly changing the partition sizes, okay? So when working with large data sets, the shuffle operation in Spark is often an expensive operation, and it needs to redistribute, aka shuffle, the data to the downstream operators, okay? So finding the right number of partitions for your shuffle operators can help tune this operation. So too few partitions, well, they're going to result in large data sizes, risking and overflowing to memory. And that will spill to disk, and that will slow down query performance. Too many partitions, back to our original problem, that'll often slow performance because you've got too many small files translating to too many small tasks, which saturate both the Spark task scheduler and the too many fetches will saturate the network I/O. So you see with this graph here, great. reduce 1, reduce 5 seems to be good size, but reduce 2, 3, and 4, those are really small. So what dynamically coalescing shuffle partitions does is that we're going to try to find the Goldilocks number here. We need to find the right number of partitions that will stay in memory, not spill the disk, not saturate the network, and not saturate the Spark task scheduler. Ugh. To find this, we can start with a relatively large number of shuffle partitions and then combine the adjacent small partitions into big partitions at runtime by looking at the shuffle file statistics. So in this example, AQE coalesces the 3 smaller ones, blue, light blue, and beige, into 1. Thus, the final aggregation needs only to perform 3 tasks rather than 5. Now, this is an overly simplistic example, but that's the basic principles behind dynamically coalescing shuffle partitions. And the key thing is that then it's okay that we start off with too large size, because we'll automatically, AQE will automatically go ahead and coalesce the smaller partitions together, so you'll have less partitions overall. So, with AQE having the ability to dynamically coalesce shuffle partitions, you've reduced the overhead of improving the query performance. But what about if you have the exact opposite problem? Instead, you have a single partition that is larger than many of the other partitions combined. This is really common in data warehousing, and what you have here is basically a skew. And when you have skewed data, that is already painful enough. When you do a join, that results in some pretty lousy performance. So, for example, we're going to take out this example. Look at table A and table B quickly here on the left side. Okay, it's very apparent that table A part 0 is going to be the bottleneck, the one in red, right? Because all the data, for example, maybe a null value in your a la data warehouses, all the values are in part 0, right? The red here. Okay, so what will end up happening, this will result in long running or frozen tasks, a lot of disk spilling, and very low resource utilization in most nodes, and possibly even out of memory errors. Okay, and so, table A, B, part 1, part 2, part 3, all those, they work perfectly fine. But when you look at table A, part 0, yeah, that's going to slow things down. All right, so now a common approach is to solve this by rewriting the queries and finding, skewed values. Or rewrite the queries to handle the skewed values by adding extra keys or forcing a repartitioning. Okay, so that's not the funnest way to do things. So what we're going to do here instead is say, let's see if AQE can solve our data skew problem. And how it does is basically it'll detect the skew from the partition sizes, okay, and use the running time statistics after executing stages 1 and stage 2. All right. Then after it does that, it'll actually kick in a skew reader, right? The query is optimized, and then the skew shuffle reader kicks in. This is on the right-hand side now. It will, because the skew reader kicks in, split the skew partitions into smaller subpartitions. So for any of the shuffle partitions that are too large. So instead of you changing your code base underneath the covers, AQE is going to go do that for you. So let's go back to our original problem of table A part 0 here in red, which contains the skew. Well, like we said, after realizing the partition is too large, AQE will add the skew reader to automatically split table A's partition part 0 into 3 segments: split 0, split 1, and split 2. Then it will also replicate table B part 0 to align with the splits that you've seen here. Okay, that way you can have more narrow transformations. You can minimize shuffling, so they're all aligned together. So after this step, we can parallelize the shuffle reading, sorting, and merging for this big partition A0. By avoiding to generate a very large partition for the sort merge join, we've significantly improved the query performance. In fact, when we talk about query performance and look at AQE, and we're going to specifically talk about TPC-DS data inquiries, AQE yielded up to an 8x speed in query performance, and 32 queries had more than at least a 1.1x speed up. Okay, the chart here is about 10 TPC-DS queries that have the most performance improvements by AQE. And as sort of implied before, as the Spark community progresses, we will continue to improve the compiler and introduce more adaptive rules. So that was just AQE. So let's talk about the next performance feature that we want to highlight here is another runtime optimization rule, okay? Dynamic partition pruning. The key principle of dynamic partition pruning is to avoid scanning the entire partition by using the query results of other query fragments. This is particularly important for data warehousing and OLAP type star schema queries that result in significant performance improvements in TPC-DS performance, and for that matter, significant improvement in any of your data lakehouse queries. So, for example, when referring to the TPC-DS benchmark, 60 out of the 102 queries shown show a significant speed up somewhere between 2x and 18x when comparing with or without dynamic partition pruning. So, pretty sweet. Right, so it seems to me that this is something we probably want to keep. All right, so what's going on underneath the cover? So let's first start before we ever ran the optimization. Okay, so when working with large data sets in Spark, if you can remove any partitions that are not needed for the query before you run the query, you can significantly increase the performance of that query. For that matter, that happens just about any system anyways. After all, if you're querying less data, you don't need to scan all the data, you're just scanning a subset. So this is particularly important for data warehousing and OLAP type queries, where you're often joining and filtering data for your aggregate queries. So let's start with an example where we are doing a join between table 2 and table 1, as noted in the select query here on the left. All right, so if we perform a scan on our dimension table 2, table 2 is our dimension, table 1 is our fact, we're going to basically, as I said here on the left side, it's dimension table 2, we're going to filter out on only the needed values, right? But what happens with table 1, right? After all, we're using the join and we're going to go ahead and filter out because you have the AND clause, all right? But in table 1, without dynamic partition pruning, it will perform a full scan on table 1 with all of its partitions. And table 1 is the fact table, so it's a large table. So the whole context here is that with dynamic partition pruning, Spark prunes the partitions in fact table 1 by identifying the necessary partitions that result from filtering dimension table 2. So notice how the join statement here involves fact table 1 and dimension table 2 joined by P key, but the filtering of table 2 is by ID. Okay, so thus to dynamically prune the partitions of fact table 1, first we need to do a filter push down on the left hand side. So you'll see it in red here on the left hand side, the filter push down. So we can generate a new filter on the right hand side. Okay, so Spark will identify the P key values from the join to identify the filter and so the associated applicable partitions in fact table 1. This is done basically by reusing the query results from that left side and then generating a list of constant values, okay, the P key values from fact table 1. So the basic mechanism for DPP is inserts a duplicated subquery with the filter from the other side, the left side, when the following conditions are met. 1, the table to prune is partitioned by the join key, or the join operation is one of the following types. Okay, the inner left semi, left outer, and right outer. Okay. We can also enable partition pruning directly in the broadcast by using the in clause with the subquery and using intermediate estimates. All right. So with that, now we can push the filter to the right side to avoid scanning all the partitions of fact table 1. So now you'll notice that because we've got the dynamic partition pruning filter result here, we can filter and scan. So we're only scanning the required partitions of table 1 as opposed to scanning all of them. So in this particular example with dynamic partition pruning, we avoided scanning 90% of the partitions, thus achieved a 33x improvement in performance. So that is pretty amazing, actually. All right. So the last performance feature is join hints. And join hints are very common optimizer hints, and it can influence the optimizer to choose the expected join strategies. So previously, we already talked about broadcast hash join, all right? But in this release of Spark 3.0, we also add hints for the other three join strategies: sort merge join, shuffle hash join, and shuffle nested loop join. Now, before you do anything, please be very careful when you're using these. It can be difficult to manage over time as it's very sensitive to your workloads. If your workload patterns are not consistent, using these hints can make your queries even slower. Okay, so really be careful here. Okay. So here's how you can use these hints in SQL queries. And notice that, don't forget, you can use the data frame API as well. So for example, going back to how this works, broadcast hash joins, right? It requires one side to be small, no shuffle, no sort. It's really fast. The key issue, of course, is that you have to make sure that one side is small, all right? The sort merge join, which is in essence the default, it's really robust. It can handle any data size. It needs to shuffle, but it needs to shuffle and sort the data, and slower in most cases when the table size is small. The reason why we often default to that is because often, more times than not, when you're working with Spark, the joins themselves involve joining two very large tables. So that's why the robustness of sort merge join is awesome. And that's why we pretty much always default to using that first. Okay. If you can also use a shuffle hash join. Basically, you need to shuffle the data, but you actually don't need to sort. Okay, so that's pretty cool. Okay, so if you've got a case where basically the sorting is not needed and only shuffling, this is a really good idea. It can definitely handle large tables, but if your data is skewed, you're going to typically run into out of memory errors, because don't forget, the sorting itself helps us identify the skews, and then because we have dynamic skew joining as part of AQE, we can automatically take care of that. But if you explicitly say shuffle hash, you're basically giving a hint to tell Spark that it doesn't need to worry about the sorting, and then if you've got skew data, then you're going to hit those out of memory errors. And finally, there's a really cool one, which is shuffle nested loop joins. Okay, it actually doesn't require any join keys at all, but that's because it's really a Cartesian product of the tables. So whenever you want to do a Cartesian product between two tables, perfect. That's where shuffle replicate and nested loop join is actually exactly what you want. But again, remember, that's the context, right? So it's actually a Cartesian now. All right. Okay, so now we're going to switch gears a little bit. We talked a lot about performance. There's also other things, but now let's talk a little bit about extensibility and the ecosystem. This release of Spark 3.0 actually includes really cool things like Data Source v2 API improvements, Java 11 support, Hadoop, and Hive 3 support. Okay, so pretty crucial and good stuff. All right. So let's do just a quick primer on the Java 11, Hadoop 3, Hive Metastore support. Okay, just as we called out, it includes Java 11 support, and don't forget, Spark 3.0 currently builds with Scala 2.12 now, so we're currently on that version. Oh, as a side note, Spark 3 did deprecate Python 2 as it's already, the end of life. Python 2 is already end of life. Okay, so Viva to Python 3. All right. In addition to Hadoop 2.7 and Hive 1.2 and Hive 2.3 support, Spark 3 supports Hadoop 3.2 and Hive.2.3, which supports Java 11. As well, Spark 3.0 supports Hive Metastore versions from 0.12 to 3.1. All right. But let's redirect for a moment to Data Source v2. All right. There are many motivations for improving the Data Source API that was initially released in Spark 1.3. So, for example, the Data Source API, its compatibility was dependent on the Data Frame API, okay, an upper level one. So it actually can't leverage the lower level APIs. It can't leverage the dataset API. So it was inherently slower because it actually wasn't using any of the high performance characteristics. Okay. Things like the physical storage information, like when, for example, partitioning, sorting, this wasn't propagated from the data source and to Spark, so it wasn't even used in the Spark Optimizer. So in other words, you could have actually had some really smart partitioning, indexing, sorting, whatever else in whatever data source you're accessing, but Spark Optimizer wasn't going to see it and wasn't going to make use of it. So it was sort of just a dumb extract from a lot of ways. The extensibility was not very good, and the operator pushdown capabilities were really, really limited. And it also lacked a columnar read interface for high performance. So, that's already pretty bad. But the really kicker was basically the write interface was so general that it actually didn't support transactions, right? So if you think about that, you have a data lake, you want to basically have a write interface that actually would have transactional support. And why? Well, because you want to ensure that your Spark jobs, when they're executing, they either complete or they fail cleanly, right? You don't want a case where basically the job runs, one or two of the tasks fail, but you don't know, and all the other tasks, like let's say you've got 20 of them and they're writing to storage, you don't want a case where because the two tasks failed, they retried and still failed, now you can't identify which files were actually new and clean and which files that were generated and created were actually old, so you want to keep them, and which files were put in there but actually end up failing because of the two tasks, so it got corrupted, right? You don't want a case where you don't know which data is right. All right, so either the job completes cleanly or, for that matter, fails cleanly, so that way you know how to clean it up. All right. If you have multiple potentially conflicting jobs modifying your table, let's just say two streaming and a batch query, all trying to run against the same table, you want those jobs to be protected within a transaction, so that even if you're running the equivalent of an update, an insert, and a delete all on the same data at the same time, okay, not just same partition, or same file, literally same row for that matter. So that's why I say same data. You want to know which job completed and also which jobs had failed, so they can retry after reassessing the changes to the table. So for sake of argument, let's just say an update, insert, delete all happen at the same time. The delete end up winning out. You want the delete transaction to complete, it to be known by everybody that it completed, number one. And number two, that the update and insert goes ahead and says, okay, got it, it failed. So now the clients that are running the update and insert can actually reassess before trying to do an update and insert on that data. That's actually what you want. Okay, so the other key aspect of data source v2 that I like discussing is that, like I said, we have the transactional support, right? And then we're going to switch over to Delta Lake real soon to dive into that. But we also want a catalog API, okay? It allows users to register their own catalog implementations and take over the metadata operations. This can give the end users a much more seamless experience to accessing their external tables. So now end users only need to register the catalog once, right? And then access and manipulate the tables in a catalog directly. While before, end users had to register each table, right? So now, if I'm doing the create or the alter, I want that information in that single catalog. All right, we're going to get back to those concepts real quick, but now we're actually going to do a segue into Delta Lake, okay? And we're doing the segue because it's the integration of Delta Lake 0.7 and Spark 3.0. It's the first release. Delta Lake 0.7.0 is the first release on Apache Spark 3.0 that adds support for Metastore defined tables and SQL DDLs. All right, so pause for a second. You'll recognize we were talking about data source v2, and we're just talking about the catalog APIs. Well, now they're going to kick in right now for what we're talking about next, even though we're talking about Delta Lake. So with Spark 3.0 metadata support, you can now define your Delta tables in the Hive metastore and use table names in all your SQL operations. So that's really good, okay? But you don't just want to do create and alter, right? In traditional distributed systems, for example, if I want to do a delete, this would actually involve selecting all the data except for the data that needs to be deleted, inserting this data into a new set of files, deleting the original data, and then pointing the table to the new set of files. And you would need to do this yourself. You actually have to run all these queries yourself, all right? So, and don't forget, this is just delete. Executing updates and merge statements is even more complicated. But because of the integrations with Spark 3.0, Data Source v2, and the catalog APIs, Delta Lake now has SQL support for deletes, updates, and merges. So, and by the way, a merge statement is basically an insert, update, delete, and deduplication all in a single statement. So definitely be on the lookout for merge. It's a pretty powerful operation, okay? Oh, by the way, as of Delta Lake 0.6.0, the merge operation also goes ahead and includes schema evolution. So it's pretty cool. All right, so, but one of the more common questions you're going to ask is, well, great, I've got these DMLs, but what's really happening on the covers? After all, I just mentioned that a delete, you actually really have to do all these other steps, right? You're going to have to grab all the data that you don't want. In other words, you're basically excluding the data you want to delete, but you're grabbing all the other data. Then you're going to need to write it down. You're going to delete the original table, actually remove it, and so forth, right? So what happens to the storage system? Because, great, I've got these DMLs, but what's really happening? Are you just obfuscating the fact that I'm doing all this over again? After all, if I'm doing all these steps that I just mentioned, and like I said, if I do the update or delete or merge immediately, do I write out Parquet files? And then do I basically go ahead and saturate the disk I/O, the storage I/O when I do it? And so the quick answer is that any changes to the underlying system, whether they be any of these DML operations, DML is data manipulation language. So update, delete, merge. The key aspect is that it results just with the addition of new files. So new files are created. All right. So whether it's a delete, an update, or merge, we're just going to create new files. And you're going, wait, well, if I'm deleting stuff, why are there new files created? So let's talk about that for a second, okay? So, as Delta Lake's writing new files every time, this process is not as storage I/O intensive as, for example, a traditional delete, which, would have required the I/O to delete the file, to read the file, remove the deleted rows, and overwrite the original file. Instead, Delta Lake deletes the data by automatically selecting all the data that was not deleted, very similar to the first step, okay, the first one. Create new files, again, very similar. And within the transaction log points to these new files. Okay, so that's the key difference. So there's a transaction log that actually tracks. So before, if I go backwards here, V1, the transaction log here on the left side is pointing to V1 of the set of files that we have. Because we created new files, now we're in V2, the transaction log flips to V2. So whenever I'm querying the data, I can go ahead, using Delta Lake, I first, underneath the covers, in other words, you're actually not doing this yourself. Spark and Delta Lake is automatically doing for you. When you're running a select, insert, update, doesn't matter. It'll first hit the transaction log to find out what's the current set of files that I have to work with. All right? And then it'll go ahead and basically point you to those files and those files only. Okay? So because I've got this transaction log, which identifies these files, it's not nearly as storage I/O intensive because I'm actually not doing a list of all the files, okay, from your distributed storage, which can be, really IOPS intensive. It can be time consuming and usually both, okay? So through its transaction log, Delta Lake can automatically obtain the necessary files. And then in addition, deletes actually at the partition boundaries are performed as pure metadata operations, so therefore they're really fast. So that's great. Now I've got a much faster way of doing this. Well, we've actually got a pretty cool trick up our sleeve because of this. Because we actually were trying to avoid the IOPS issue, we just constantly added the transaction log with these additive files basically means data versioning. Okay, so there's a small modification to your SQL statement. So for example, select star from events version as of 2, or you can also use timestamp clause. You can go back in time and review previous versions of your data. So whether due to mistakes or GDPR compliance, you can properly track and even roll back to different versions, which is really, really nice. And now you're going to say, hey, wait, well, that's great. You've got different versions of the table. I can roll back, but then doesn't that mean I'm just going to have lots of files in both the log and also in the data itself because I'm basically replicating the data over and over again? Well, yes, you absolutely are. So an important aspect is actually the ability to control table history retention. So as part of Spark 3.0 and Delta Lake 0.7.0, you can actually set your table properties by using the alter table table properties. So you can enable or disable or configure many of these features of Delta, such as automated manifest generation. So for example, log retention duration controls how long the transaction log history is kept, right? By default, it's 30 days. But you may want to alter it for your requirements, such as DPR, historical context, or whatever else. Okay. Another example is deleted file retention duration, which controls how long ago a file must have been deleted before it's a candidate for vacuum. So what happens that, remember, when we delete, what we did was just simply, it was a tombstone, and we simply go ahead and create new files. Well, now that it's been deleted, it's an older file, but what we're saying is that, okay, you're going to run a vacuum. Okay, that's a command that you run to basically clear out the older files. So if the files are older than 7 days, then the vacuum will clear it. Perhaps you want to change that default from 7 days to another value, depending on how much storage you have to work with. Okay, so this is an important aspect, so that way you can easily maintain the size and ultimately the cost of your Delta Lake. Okay, and now, like I said before, to enable these cool features, you're going to need to enable data source v2 and catalog API integration. That's why we, as talking for Spark 3.0, that's why we segued right into this, because you basically turn on Spark SQL extensions, the Delta Spark Session extension, and also the Spark SQL catalog, specifically the Delta catalog one. When you set or create your Spark session with those values, boom, now you've enabled data source v2, the catalog API integration, and so that way it'll work cleanly with Delta Lake 0.7.0. If by chance you're working on Databricks, you don't have to run these because we automatically have these turned on for you, by the way. Okay? So at this point, we've been discussing how the improved SQL support in Apache Spark 3.0 and how Delta Lake 0.7.0 enables Spark SQL DDL, DML, and Delta Lake. Okay? To take advantage of these features, it's important to also build a data quality framework as you continuously process your streaming and or batch data. Here, what you see here is the Delta Medallion architecture framework for data quality. We start with a fire hose of events that are written to storage as fast as possible as part of your data ingestion process. This is where the data lands in these ingestion or bronze tables. Okay, that's why we call it a medallion. As you refine the data, joins, lookups, filterings, deletes, etc., you start creating these silver tables. Basically, these are sort of like your staging tables if you were thinking almost like data warehousing style. Okay. Finally, you have your features for your machine learning or AI or your aggregate tables, joins, group bys, insert, update, merge, whatever. But these are known as your goal tables to perform your analysis. So typically what your BI tool is going to go query against. So what you'll notice here is that there's a similar analogy to how a data warehousing framework would kick in terms of it also, when you build a data warehouse, has its own data quality framework. And so the data quality framework for the Delta Medallion architecture is similar to that exact same concept. And this is why we talk about this Lakehouse paradigm, okay? So, like I said, we discussed about all these things, all right? About how the performance enhancements improve DDL and DML support, and the transaction guarantees are provided by Delta Lake. But because of the transactional design, Delta Lake is able to address data pain points, that are not available in traditional cloud data lakes, including some of the examples that I gave you, like time travel or DML, update, delete, merge operations, efficient streaming of I/O, caching. I know that sounds funny, but because the modifications of anything, your DML, it's all additive. The cluster actually can go ahead and safely cache the files because, well, we're only adding new files. We're actually not modifying any existing files. So things like supporting schema evolution enforcement, because the schema of your Delta table is actually stored in that transaction log. Okay? So together, these features improve both the manageability and performance of working with your data in cloud object stores, and this is what we mean by enabling the Lakehouse paradigm that combines the key features of data warehouses and data lakes. Standard DBMS management functionality, directly against low-cost object stores, right? And so this is the reason why when you work with Apache Spark 3.0 and Delta Lake 0.0, now you're able to jumpstart your Lakehouse. If you want to build your own Delta Lake, by the way, check us out at delta.io. And so let me leave you with this before we go into questions. Try out Spark 3.0 and Delta Lake using Databricks Community Edition at databricks.com/try. There are notebooks talking about all of these concepts, whether it's Spark 3.0 to time travel to schema evolution. They're all in the Databricks GitHub under Tech Talks. Okay, and for that matter, talking about Tech Talks, join our Tech Talks. We have a data and AI online meetup at this URL, so come join us. We usually have 1 to 2 a week, talking about a range of topics, whether it's from MLflow to Delta Lake to Glow to genomics to even COVID-19 analysis. So come join us. Don't forget, get the free O'Reilly Learning second edition ebook at dbricks.co, get-ebook. And don't forget to read the VLDB paper, Delta Lake, High Performance Asset Table Storage over Cloud Object Stores at delta.io. So thank you very much for your time, and love to go ahead and answer some of your questions.